Hello, Internet! Today we're gonna code knowledge graphs. And the first thing that you see here, remember last time I showed you the deep graph library, DGL, based either on PyTorch or on TensorFlow. And we had a look at the different modules, and now we have here also the source code for a knowledge graph. So you think, hey, great, there's the code for the knowledge graph. So we have our knowledge graph data set. It has some form. This is great. We notice that we have a start, a relation, and a tail, or a head, a relation, and a tail. And then we have here build our knowledge graph, create a DGL homogeneous graph with heterograph info stored as node or add features. And here's the code to do the embedding of the graph. So perfect. Let's apply the code. Well, I have to tell you, not so fast, not so fast. At first, we have to understand a little bit what mathematical algorithms are embedded in this code, why we need it, and what the hell is a knowledge graph. Now, the definition of a knowledge graph, let's say, is a directed, heterogeneous multigraph whose node and relation types have domain-specific semantics. So you have a lot of relations going on between the different nodes, and you have a free definition field for your relation, and you can encode a lot of information for each node. And a knowledge graph allows us more or less to encode the knowledge into a form that is human interpretable, and we can use automatically for analysis and inference. So where to go next? The knowledge graph embedding. You might say, okay, this is great. By the way, the code, if you're interested, is there's a GitHub from awslabs, and it's called DGL, Deep Graph Library Knowledge Graph Embedding. And this is here the documentation on the knowledge graphs. We can start here. Knowledge graphs are data structure that store information about different entities in their nodes and about the relation in the edges. Is to compute the knowledge graph embeddings. You remember with the normal graph that were not the complex knowledge graph, but a simple monodirectional graph structure, for example, we calculated the embedding in a lower dimensional vector space to reduce the complexity and to fasten our compute time. Now, if we have a multitude of relations going on between a multitude of nodes, and the information in the nodes itself can be quite complex, this here is the generalization of the simpler cases. Of course, this package is built on top of the deep graph library I have showed you in our last video on knowledge graphs, and this is the special module KE for knowledge graph embeddings. And here we go. We have our platform in the cloud. You have one or more GPUs, one or more CPUs. You have a cluster up and running. You have a PyTorch or a TensorFlow. And then, of course, you have your runtime. But the nice thing is that we already had a look at those knowledge embeddings. They have an idea behind. They have a mathematical formula behind. And let's find here, I'm looking for a sentence. So here the knowledge graph embedding are computed so that they satisfy certain properties. And these models define different core functions. And those core functions, they measure the distance between two entities relative to its relation type in the low-dimensional embedding space. And you might say, okay, so this core function that measure closeness, as we already have seen here, are trans E and trans R. I already showed you in our last video. And now you can have quite a lot of other more complex functions for measuring dimension in the low dimensional embedding space. So here we go, a quick start, the performance, scalability, beautiful. Yeah, Cited, this is here from 2020. This is from publisher is Association of Computing Machinery in New York. Proceedings of the 43rd International ACM SIGII Conference on Research on Information, and these are the authors. So this is the citation done. Have a look. It is really great. We are running here on version 0.1.1. So you know, oh wow, we're here in development land, deep in development land. And as they tell you, there is some documentation. Let's have a look at the documentation. Either you go for here, I leave you the link in there, or you have the same here. This doesn't matter at all. And we are interested now in knowledge graph embeddings. And as I told you, what is a graph? What is a knowledge graph? Scenario, you can have a lot of relation between, for example, between Tom and Mary and whatever, sister, brother, what they're eating, what is their dishes, where they're living, where there's the city, if they're Canadian, and what is their workplace and whatsoever. You can see here we have a lot of links between our nodes. And what is the task of knowledge graph embedding? Let's repeat. Embedding is the task of completing the knowledge graph by probabilistically inferring the missing arcs from existing graph structure. Probabilistic, so you know, probability, yippee, you will say. Statistics is finally back in full swing. So we have a multi-relational and more complex model and expensive, definition. We have here, yes, core function. Here we go. So this is the core function for our different models. Trans E and trans R we had in the last video. And now you see you have here from Rascal and different other models, different core functions who measure a little bit more advanced way if you want. What is the common? This core function measures how distance two nodes relative to its relational type. So a short explanation of core function. And the fact, no relation is there. We desire to project a sparse and high-dimensional graph representation vector space into, and this is it, into a lower dimensional dense space. Also, hopefully a topological space with, or even a vector space. So this is similar to the process used to generate word embeddings. You see, we always come back to our old methodology, to the old recipes, and now we do this on a multigraph structure. Trans E, I showed you the last time, trans R. Yeah, Rascal is now a bilinear model, so it gets a little bit more complicated, and complicated you can have a look here. But this is not what we are interested in. As you can see, we have, again, negative sampling to shorten our compute time. We have loss functions. And you can see you have here different complexities, core function, embedding for all the different methods. Beautiful. So you jump right in and choose whatever you need, whatever you are looking for. But before we start coding, there's one thing I want to show you, the theory. And you might say, finally, God, yes, here we are with the theory. I was looking for it. And the best source I found on the internet is still Machine Learning with Graphs by Jure Leskovich, Stanford University. The course is CS224W. This is the 2021 edition of his slides. And it is about knowledge graph. 86 pages, introduction to knowledge graph, completion, we have a look at path queries, and then of course we have a look at box embeddings if we want to optimize our graph embeddings. So you know the knowledge graph, the nodes, the relation, the information you can store in the nodes. We said that the nodes we can call now entities, and then the node labels have types, person, thing, car, mountain, whatever, and you have relationship. You can have different complexity. You have your social networks, your Google Graph. Almost now a decade, you have Google Knowledge Graphs. The application, the question answering. Yeah, maybe a good time. The application of this technology is primarily to answer question. Let's say if you ask Alexa and you have a complex question, maybe the answer you get is exactly done by calculating a knowledge graph. So let's have a look at it. Yeah, this is so what we are looking here. We have a graph given, and then one task, for example, is have a look at the missing relation in this graph. Have a look at the probabilistic functions. What has the highest probability? What is missing here? And you see here for an author, the relation to a particular branch, to, for example, science fiction genre, you can deduct. Again, the representation of in our knowledge graph are triples. We have the head, the start, our starting node. We have a relation, for example, is married to, and we have a tail, and this is the target node. The key idea, again, we model the entities and the relations in the embedding space in the vector space R. And D is a lower dimensional space, and therefore we can accelerate our computation. Now, as we had a look at last time, if we do these embeddings, we have to answer two questions: how to do the embedding, and what the hell is closeness? What is the distance matrix in this space? How can we calculate closeness? Again, symmetry, very beautiful. Yes, trans E, trans R. We had a look last time. We're not gonna run over this again. Just show you. I'll leave you a link for those slides again. You can find those slides also in the description of the other video. And now path queries. Path queries are a very simple type. So we do some multi-hop reasoning, and we want to answer some complex question. So let's do this. We have a one-hop query. Where did a particular person graduate? Which is his university, alma mater? Or there are some even more complex questions. Where did Canadians with a specific award graduated? So we have that they have to be Canadians, we have that they have to have a specific award assigned to them, and then we are looking for a particular subset where we find out who this person were and where they graduated, what the alma mater was. So you can see here, one hop, yeah, this is of course. So our computation graph, we start from a node and then we go to another node and then we add it. So we add different segments of a path, adding more relations on the path. So the path queries can be represented exactly by just adding all the different queries. And the computation graph of path queries is a chain. Yeah, how to answer this query, of course? Well, we have to transform into our embedding space and do the calculation over there. So this is the different path and the different results. Incomplete, path question, dense graph. Yeah, this is so. The idea again is we embed our queries. You know that we have embedded our knowledge graph representation, and now we embed queries. And we generalize our trans E to multi-hop reasoning. So our query here is from here to here, from here to here, from here to here. And then finally, this is in a vector space, our query. And then we are simply looking, hey, given an answer V, we just calculate the nearest neighbors, for example, or the norm between Q minus V. And we find out how to optimize this function so we receive a minimum. Literature here. Transversing knowledge graphs in vector space, archive preprint from 2015. Great. So you see, this is already 7 years old already. My goodness. So computation graph, where did Turing Award winners graduate? We have here our computation graph, and have here our mapping to the embedded space. So we have here the first projection. And in embedding space, we have here an award, and the award has been won by, let's say, 4 persons, 1, 2, or 3 persons, and you calculate a mean or whatever. And then you say, if you have those persons, where did they graduate? So in the computation graph, you have another projection, but in the embeddings vector space where we do our calculation, where we find our answers, because it's a lower dimensional space with a reduced complexity, we have here now a vector from here, again, to this area in our embedded space where we have New York University, Cambridge University, Edinburgh University. So we have now a vector reaching in here into this, it's not a domain, it's not a subset, into this area of our embedded vector space. So even if we have more complex, of course, you can add path plus path plus path. This is not so much of interest because this is just an n+1. But what is interesting here is now, where did Canadian citizens with the Turing Award graduated? So we have here a multitude of sub-answer we have to discover. So we have here the people with a Turing Award. These are those subset of people. And then we have people with Canadian citizen. And then we have this subset. And you see here, the key and idea is embed the queries in vector space. We have done it. And then we take a neural intersection operator. And how we take this intersection operator in the embedding space? And this is it. Design an operator with those functions. Of course, it's permutation invariant. We had a look at this in our symmetry lesson. Yes, you have this. And the answer is, you have here the two vectors. And then from this, let's call it vicinity, we have now a vector right into the area of our embedded space where we have the university. So this is our 1, 2, 3, the third resulting vector. And this points into the area where our answer is located. So now if you say, beautiful, what are the limitations by the model? And now we come to our query to box. And this is a very visually simple interpretation. If we have now here in our embedding space, this subset of this space where we have now the alma mater, the universities where they graduated, Cambridge University, Edinburgh University, then we just construct. Yes, we have to construct a hyperrectangle, some boxes in our embedding space, given that all of those points, vectors in vector space are solutions, are valuable solutions. And then the intersection of boxes is well defined, because before it was not so easy, but if we have a box and we want to calculate the intersection of two boxes, well, that is easy. Do we have maybe a visual representation of this? Yes, here we go. So we just look at the embedding space, at the mapping to the embedded vector space. So we have here our Turing Award. We have the people that satisfy these conditions. And we have the red box, and then we have who is Canadian citizen, then we have the yellow box, and the intersection, of course, you see this is Benji and Hinton, exactly at the intersection. And from there on, yes, a little bit of mathematics, yes, we can now project this from here to our answer subspace, our validated subspace with the university, and we get our final results. So to answer a question, where did Canadian citizens with Turing Award graduate? A rather complex answer with a lot of dependencies and a lot of information stored in the knowledge graph to be able to answer this question. This is the methodology. You construct your boxes around the valid target spaces, and then you just go on from the intersection of the boxes. So do a little bit of mathematics, but there's nothing complex behind it. And you see the shortcomings we had in trans E and trans H model. Now with the query to box, we have checked okay, and okay. So here we go. For details, check this paper. I haven't seen it, but just for reference reason. Again, these are the slides from the beautiful Stanford educational series, Machine Learning with Graph. And this is CS224W course by our Professor Juri Leskovich. Highly recommend this. I will leave you a link in the description of this video so you can have a look at this. And more or less, this is it. Yes, you have a visualization. You can embed it, and you see the result is really beautiful. So, perfect. Now we are already 19 minutes into it. And now you say, hey, finally, it's time to code. And maybe we will do the coding in the next video. I see you. And for all people who stayed with me until now, here I show you a Jupyter Notebook example of knowledge graph embedding using the Wikimedia knowledge graph. And you have here, I give you the link in the description of this video, of course, where you have here the notebook examples, and you have a Python notebook that has all the instruction that guides you even through the installation of our knowledge embedding, the data preparation. Of course, the zip file has 24 gigabytes in total, so you better prepare on a machine that is able to handle this, maybe also with multi-GPU. Then you load the files and you load the entity files, and you have here all the different cells you can execute, and you understand you can follow the knowledge graph embedding, how it is done. Knowledge graph embedding, you see there's a lot of parameter you can choose of, regularization, hidden dimensions, whatsoever, batch size, multi-batching. Yeah, this is what you have to go through. But remember, this is great because you have a mix of a CPU and GPU calculation. And if you have multi-CPU and multi-GPU instances, this is great because they are optimized for CPU and GPU. But more about this maybe in the next video. So have a look at this, play around with it. This is a predefined Jupyter notebook for knowledge graph embeddings implemented in Python code. I see you in the next video.